We're now going to look at what happens when we add energy to a substance and it can undergo temperature changes and phase changes. I have supercooled ice at minus 10 degrees Celsius and I have 100 grams. In this problem I'm going to find out what is the final temperature when I add 1.6 kilojoules, and we're going to do a series of problems with different amounts of energy. Now what we notice is we have 5 energy equations here. 3 of them, Q1, Q3, and Q5, we have a temperature change as a function of the energy, and we use the equation Q equals mc delta T. We have different heat capacities depending on whether we're in the solid phase, the liquid phase, or the vapor phase. And when we get to a phase transition, we use the molar enthalpy of fusion or the molar enthalpy of vaporization times the number of moles to calculate the Q. So when I bring the system up to 0, it's originally 100% ice. As I continue to add energy, the ice melts it. When I'm halfway across, it's 50% ice, 50% water. The temperature hasn't changed. And when I'm all the way across, I now have 100% water, 0% ice, but it's still 0 degrees Celsius, okay? Now, what you notice here is that the enthalpy of fusion is 6.02 kilojoules per mole, while the enthalpy of vaporization is 40.6. This is a much larger number, which makes sense because I'm overcoming all the intermolecular forces and the liquid is becoming a vapor. Because that is such a larger number, this would be almost 6 times longer. So we put a zig here in the graph to indicate that we've lost our scale here, okay? All right, so the first question we got to ask ourselves is how much energy does it take to raise my supercooled ice to 0 degrees, and is that number less than or bigger than 1.6? If it's equal to 1.6, I'm at 0. If that number is greater than 1.6, I have supercooled ice still, and my temperature is between minus 10 and 0. And if that number is bigger than 1.6, I've got to ask myself, have I added enough to melt it all, continue heating it, and where in this transition am I? So we ask ourselves, how much does it take to bring the supercooled ice to 0 degrees? So Q equals mc delta T. We have 100 grams of ice. Our specific heat capacity for the ice is 2.06 joules per gram degrees C. And the temperature change is always the final temperature, 0, minus the initial temperature, a minus 10, which is in degrees C, and this becomes a plus 10. And when I get out my calculator, I find that this is 2.06 kilojoules of energy. Now I'm going to write that over here in red, equals 2.06 kilojoules, because we're going to have some additional problems where we add more than 2.06 kilojoules, and we need to figure out what the final temperature is. Okay, so now I know that 1.6 is not enough energy, 1.6 kilojoules, to bring it to 0 degrees. So my final temperature is somewhere between minus 10 and 0, and I'll use the first equation, Q1. So Q is equal to mc delta T. Now, I now want to solve for the final temperature, which is equal to mc Tf minus Ti, and I algebraically rearrange this, and Tf is equal to Q over mc plus Ti. Now, Q is the heat we have added, so we've added 1.6 kilojoules. We've added this to 100 grams, which is equal to 0.1 kilograms, and I'm not going to write all the zeros in there, but that has 4 sig figs. And my specific heat capacity is 2.06 joules per gram. Now I can multiply the numerator by 1,000 and the denominator by 1,000 and not change anything. So it's the same as saying 2.06 kilojoules, 1,000 joules, divided by kilograms, 1,000 grams, degrees C. So my kilograms, and this here should have been 0.01 kilograms because I was converting 100 grams to kilograms. So kilograms over kilograms cancel, kilojoules over kilojoules cancel, and I have degrees C in the denominator of the denominator. And now I add to this the initial temperature, which was minus 10. So this temperature is 7.77 minus 10, and this was really 10.0. That number is known to the tenths position. This 7.77, I wrote an extra one here, but it really has two significant digits, so we could call it 7.8, but we're going to keep that 0.7 in there, but it's known to the tenths position. So this is equal to minus 2.23, which is equal to minus 2.2 degrees C. Okay?